this. Okay. So the rest of chapter 8 is, well, I'd say especially 8.6 is a little bit weird. But then the rest of chapter 8, we're just introducing some quick topics, right? So just like the whole of chapter 8 has just been like, here's a topic, here's a topic, here's a topic. And so we're not really expecting to be able to really do anything, but it's just having an idea of these concepts. What I did, I can't remember if that was after class last week, I think, or on Monday. I think it was after class. I extended the assignment due dates on Moodle, those quick little assignments, because I saw some people had missed them, so I just opened them up because they're just quick and they should be easy marked. So when did I assign them? Or oh yeah, Louise says thanks. You got it. Does anyone remember when I extended them to? Because I cannot. Let me see here. I've got Moodle up, wrong course, but wait.
I can see chapter 6 for April 9th.
Till April 9th. Oh, okay, so maybe what I think, yeah, April 9th, I think I extended all those, so assignments, I want to say,
Yes, April 9th.
6 to assignment, which ones did I extend?
6, 7, 8.
6, 7, 8?
Yeah.
Nice.
10 as well.
Okay, yeah, and then yeah, 8 and 9 probably.
Yeah.
6 to 9 are all due April 9th at 11:59 now. So just make sure that you do those because they're just supposed to be easy marks. Okay. So we decided that on Monday we'll just do logistic regression, which is chapter 9, logistic regression, and then we'll be all done. And then oh yeah, Sandy, hang on. Oh, thanks, Annabelle. Did I open assignment 6? Try it and see what happens. If it's open, if it's not, I think I opened it. But if it's not, then let me know and I can open it till April 9th. I know, not really fair, but to people who did it on time, but well, what can you do? They're just quick and easy anyways. So then on Wednesday, we've got our final quiz, which is just going to be a Moodle quiz. Moodle quiz during class time on material after test 2. We haven't done a lot of material since test 2, and so it's just going to be a quick little final quiz. Okay? And it's going to be 10% of your grade. And then lab 6 is due April 21st, we said. Oh, Luis is asking, where do we start our review? I'm going to try to make it as much multiple choice as possible, just so it's just a quick quiz. Where do we start our review? Test 2 went up to 7.1. So here, 7.2 onwards. Right, and I'll say mostly multiple choice. Mostly / completely, whatever I can pull off. Multiple choice. Oh, with the check option. Let's see here. That feels not like a quiz, but like an assignment. So I'm gonna go no check option. But I guess I can be persuaded, but no, let's go no check option. So lab 6 is due April 21st, and I will use your 5 highest lab grades as your grade. Sad faces coming in for the no check option, I'm guessing. That's fair. I'll see what I can, if I can come up with something reasonable. You won't be able to check your way through all the multiple choice, but what if you had 2 attempts with a check option, something like that it could do. That is getting a winky face, so that's pretty good. And a smiley face. Ew, not bad. All right. So, what was I saying? Oh yeah, so that's the lay of the land for the rest of our time together here. Not a lot of time left, just 1 week. But what'll be nice is once we've got this little quiz out of the way, then we're basically home free. We use the final exam date as your lab 6 due date, just so that you're kind of done at the same time that you were supposed to be. And that was by request. That wasn't me. That was by request. So, or suggestion, I should say. Okay. So let's keep going through chapter 8. And like I said, it's just like a little sampler of all these things that we could dive deeper into, of course, but we won't. Section 8.6 in particular really only introduces terminology, so it's kind of a weird section. They've called it repeated measures, designs and data sets. Designs and data sets. We've already seen all these things, but it really just introduces new terminology to what we've seen before, namely the between subjects and within subjects designs. Within subjects designs. Between subjects is essentially a one-way ANOVA, And the within subjects is if you introduce some blocking, right? And so here, I would say that this is kind of, if you've got a one-way ANOVA, then you're looking at the, you're comparing between subjects. And here, if you're looking at within subjects, then you've got some blocking. And so a two-way ANOVA is usually how I think of it, because then the within subjects are within each of the blocks. We're just going to write out the definitions, because that's as far as I'll expect you to take this. Of course, kind of repeated measures designs, you can balloon out and spend a whole term on it if you wanted to. And that's the same with all the rest of these sections that we're about to introduce. So we've got the repeated measures, and then we're going to talk about the relationship between ANOVA and regression. And then in 8.8, there's the ANCOVA, the analysis of covariance. So all of these, we could absolutely balloon out into a whole course. So, but for what I expect you to know, it'll just be what we're talking about here in the notes. So not to worry. So a between subjects, and I'll underline that because that's kind of the definition here, design is a one-way design with subjects as experimental units, right? So it is a one-way design, with subjects as experimental units. Okay. Each subject receives one treatment, right? So I would think of that as not repeated measures, right? Because each subject receives one treatment, and each treatment is assigned to several subjects, right? And so that's kind of our standard. You've got 20 people and you give 15 of them the drug that you're interested in, and then the rest of them, you give them a placebo, right? And so you've got this one-way design, and each person is getting a treatment. So each subject receives one treatment, and each treatment is assigned to several subjects. Each treatment is assigned to several subjects. That's when we're interested in the between subjects, right? So what's the difference between all these subjects depending on their treatment? Okay. This is essentially chapter 5, right? Where we just said, okay, we've got all these people, we're going to randomly assign them to a treatment, and then each treatment is assigned to several subjects so that we've got some sample size for each treatment. Right? It's nothing new. If we talk about a within subjects design, remember I kind of call this, if you've got blocking, right, is a complete block design with each subject as a block of units. Okay, so within the subjects is essentially within the blocks, right? So a within subjects design is a complete block design, which means what? It means we have the same sample size in each block, with each subject as a block, with each subject as a block of units. Okay. I'll add that the experimental unit is a time slot for a subject, and so right within each block, right, we assign each of the treatments, and so the experimental unit is a time slot for a subject. Okay. For example, right, if you've got do you guys remember on test 2, Shaka was comparing the 3 different exercise routines and the heart rate that they produced, right? And so each player, right, did each of the treatments. And so the experimental unit is the time slot. So day 1, day 2, day 3, whatever exercise they did on each of those days. So usually we're talking about time slots if we're talking about these repeated measures, and the blocks is the subject in this case. And so within the blocks, right, are we seeing a change in the treatments? One thing to note is that for agriculture, right, we're not talking about time. It's usually time, though, if we're using the same subject to do multiple things or to receive multiple treatments, then we're talking about time. But where we started was for agriculture. Oops. For agriculture, it is space rather than time. That gets subdivided. So this is kind of where we started. We started talking about, blocks in terms of the physical space that we're dividing. And then we kind of morphed that into, okay, well, block is just anything that you want to control for. So the different players on test 2, for example, right, those were the blocks. And then we were more interested in the activity and how it affects the heart rate. But we introduced these blocks. So in agriculture, typically we divide it into space instead of time. But it's just how we divide these blocks. Right? And so each subject provides a block of time slots. So the subject here, so within subjects, the subject being the blocks essentially, right, with each subject as a block of units. So each subject provides a block of time slots, right? Or in the case of agriculture, a block of space, right? And receives a complete set of treatments. Oops, one at a time in sequence. Okay. So we randomly assign the treatments, and each treatment each treatment is assigned to a time slot, is assigned to a time slot, right? Or physical space in agriculture. So here, I would say this is basically all we need to know. All we need to take away from 8.6 is this terminology. It's nothing new. We just haven't been calling the studies between subjects or within subjects. Essentially, you have between subjects if there's no blocks, and then within subjects if there's blocking, because then you want to look at how the treatments behave within those blocks, right, where the subjects are the blocks. And so that's basically all I need you to take away from this section. If you're curious, there's also a section on crossing factors, but I'm gonna ditch that because it's not actually that important. It's essentially introducing the interaction term, but just different terminology. But for I'll put complete example in quotes because it can never be complete. See example 8.18 in the textbook. Okay. This stuff is just in case you have any questions about this terminology. But as far as what I want you to know for the quiz especially, it's just the difference between subjects design and the within subjects design. What does it mean if we've got between subjects? Well, it means that there's essentially no blocks, and we're just so each treatment is assigned to several subjects. Whereas if we're looking at within subjects designs, then we're looking and comparing within each of the blocks. Right. And so this is more not testable, right? That's just if you want to know a little bit more about it, right? Or if you want to just emphasize some of the concepts, right? So some of that terminology. Okay. So I'm going to check for questions here, but I don't really see any on this, my second screen. So let's see here. Nope. Just sad face, winky face, smiley face. Okay. All right. So 8.7 then is going to be the link, and I'm just going to show you just briefly the link between Anova and regression. So we can run Anova essentially. So Anova and regression with indicators, and regression with indicators. Okay. So one important thing is that Anova, remember Anova has a response. Anova has a numerical response with categorical, not really predictors so much because that's regression, but categorical explanatory variables. We'll start with 1, but then we can build out to 2, right? If we've got a blocking, and then and then the interaction term. Whereas regression is also for numerical response. Oops, response. And typically, numerical or predictors, and typically numerical predictors, right? But we can use categorical predictors. Oops. We can use categorical predictors, and we just started introducing the indicators. I want to say in maybe late chapter 3 or maybe even in chapter 4, where we said, okay, well, we can use categorical predictors if we introduce indicator variables. They're also called dummy variables. Oops. Indicator or dummy variables. Indicator variables sounds nicer, so I prefer to use that, but dummy's fun too. So what's important here is, okay, well, the link between ANOVA, right, where we've got this categorical explanatory variable, and regression is that, okay, well, we've got a numerical response, so we're on the right track with the responses, right? But as long as we use categorical predictors, right, we will be able to link up these categorical predictors to these categorical explanatory variables, potentially, in ANOVA. So, but we do have to introduce indicator variables. So an indicator variable is 0 for no and 1 for yes, right? And depending on the treatment that we're talking about, either they didn't get the treatment or they got the treatment, right? And then it's kind of an on-off switch here to indicate if that category is there or not. So what we're gonna say is recall, and this was at the very end of regression, so I'm saying recall, but it was just very brief. It was one of these sections in chapter 4, I'm pretty sure. But recall that if we have a categorical variable, with more than two categories, right? So 0, 1 won't work anymore. Right. So if we have a categorical variable with more than two categories, we create indicator variables. For I minus 1 of the groups. Right. And we use I minus 1 because the last one, or the first one, or one of the groups, or categories, groups or categories, is left as a reference group, or is used as a reference group. So we did talk about this just very briefly, and now that I think about it, we didn't quite finished chapter 4, so I can't remember if we actually talked about it, or if I just wrote notes and we didn't get a chance to talk about it. But anyways, so what we do if we have more than 2 categories, then what we have for each category, right? So say our variable has categories A, B, C, and D, right? We would create an indicator for A, which is 0, 0 if it's not A, which means it's either B, C, or D, and 1 if it's A. We would create an indicator for B, where it's 0 if it's not B, so if it's either A, C, or D, and 1 if it's B. An indicator for C, and this is tedious, but it's once you know what you're doing, right, then it's not that bad. The indicator for C is 0 minus 0 if it's not C, right? So meaning it's A, B, or D, and 1 if it is C. Save the indicator for D as a reference group. Right, we need to start somewhere. And so we use D, yes, it is D as a reference group, as a jumping off point. And then we either switch on a, switch it on, switch it off, switch on, switch off B, switch it on, switch it off C. And then, but we use D as a reference group. Yeah. So one thing I've kind of gone rogue on my notes here, so let me just make sure. So just as a little kind of summary here, we've estimated the effects using sample means for various levels of the factors. So far, right, in Anova, right, and maybe that's how I should start. In Anova, right, we have estimated the effects, so we're pretty comfortable estimating the effects. We've estimated the effects but using sample means, for various levels of the factors, But we could also fit them using regression with indicator variables, just like we talked about here with indicator variables, to identify the categories of each factor. So, but we could also fit them using regression, with indicator variables, to identify the categories of each factor. So to identify the categories of each factor. Okay. So what I want to do is I want to show you a comparison, right, between Anova and regression. right? So we're going to look at Anova output, and I want to show you some regression output and show you the links between the two, and kind of womp womp, and not really that surprising. We could use either Anova or regression, but if you have a categorical variable, it will be easier to use Anova. But depending on the situation, you might want to use regression still with some indicator variables. And what I'm going to show you is that you'll land on the same results, right? And so we get this very kind of conjoined set of outcomes, right? Whether we run an Anova or a regression with indicator variables, we're going to land on the same results. So I've got, I think, did I put them here? One-way Anova, okay. So the first thing is we'll compare a one-way Anova, and I'll just put it in our notes here. Compare one-way Anova output, one-way Anova output with regression output. And so here, this is the fruit fly data. I'm not sure if we've talked about the fruit fly data, but you've definitely seen it if you're reading along in the chapters. But so the fruit fly data, we've got 5 categories. So we want to look at the lifespan of fruit flies if they live with 8 virgin other fruit flies, 1 virgin fruit fly, 8 pregnant fruit flies, 1 pregnant fruit fly, or the control group if they just live alone in some sort of jar or whatever habitat they've got for them. So the mean lifespan is, if they live with 1 pregnant fruit fly, is 64.8. With the 1 virgin, it's 56, and then the mean with 8 pregnant other fruit flies, it's 63, very similar to 1 pregnant. 8 virgins, significantly, well, I shouldn't say significantly, but quite a drop in the expected lifespan or in the average lifespan if they live with 8 virgin fruit flies. And then just as a control, 63.56. I think it's days, but I can't remember. And so we're looking at the mean lifespan of these 5 groups, 1, 2, 3, 4, 5. So here we've got our sample means, we've got an F statistic, we've got a p-value, so we know that there is at least one of these groups is different from the others. So here, oops, F is 13.61 with a p-value of roughly 0.000. Right. So we conclude at least one of these treatments, is different from the others. Okay. So we've got our sample means. This is how we would estimate the treatment effect, right? And so we've got our overall mean, but then we're going to look at these treatment effects, how they jump from the overall mean to each of these individual mean estimates. Okay. And so what we've got is, if we run this as a regression, right, then what we have is we've got this regression model, right, with each indicator variable, 8 virgins, 1 virgin, pregnant, 8 pregnant, and 1 pregnant, and then the none is going to be your reference variable or your reference group. Okay. So here, we'll bring this data set in, or this output in here. So this is our regression output. Regression output, of course. And what we find is that we're using the none category as the reference group. Okay. So what we'll see here is that, okay, if we go, there's a couple of interesting things to keep in mind here. Well, we get the same F value down here, right? So that's not surprising, especially in the one-way ANOVA case. That's not that interesting. But one thing that we will find is, where's that? I don't think it's on this output. Okay, so what I wanted to point you to first then is that these means, right? Noticing, and I'll use maybe different colored highlighters, 63.56 is the coefficient of the constant because that's your reference group, okay? P1, right, so 1.24 says, okay, from the reference group, you're gonna add 1.24 to get the estimate for P1. And so the estimate for P1, let's see here, P1, 64.8, 64.8 should equal, let's see here, this one and this one. So it should equal 63.560 plus 1.240, which hopefully when I do it, 63.56 plus 1.24 puts me at 64.8, which is what the mean is there. And so you can do the same thing, just remembering that you're going from the reference group, and then for V1 for that group mean estimate, then you subtract 6.8. Here you subtract 0.2. Here you subtract 24.84. Right, and so here we can find the estimates. We can find the estimates for the means. The estimates for the means using the coefficients. So you can do the same thing, right? If we highlight, let's use a different color here, maybe blue, 1 virgin. So 1 virgin, 56.76 should be the control, 63.56 plus, and let's see here, we're talking about one virgin plus negative 6.80, plus negative 6.80, which is, so 63.56 minus 6.8 puts me at 56.76, which is that number that we were talking about. All right, and so having the regression output, right, eliminates the need for these estimates, or vice versa. I would say we should probably still use an Anova here. It's way more telling, I would say. But there is a lot of overlapping information here, right? And same thing here, especially for the one-way Anova, we get the same F value. Okay. There's another thing here. Let's see if I can find it. I think it was in the previous example. That's okay. Oh, that was just if we had one. No, that's not interesting. Well, I guess now that I've said it. No. I don't want to cloud your heads. But I do want to talk about the two-way ANOVA. So the two-way ANOVA is if we've got something like this, right, where we're talking about, so this is the pigs data that we've talked about before. We looked at giving pigs antibiotics in combination with B12. So some pigs got antibiotics, but not B12. Some didn't get antibiotics and not B12. Some got antibiotics but didn't get B12, and so on and so forth. So there's 4 different combinations here. And so we've got these different F statistics for the antibiotics and the B12. We also know from our analyses earlier that there is an interaction term, so we'll introduce that in a little bit here. But if we've got this two-way ANOVA information, so I'll just put a note here that we've got two-way ANOVA. Oops. Okay. What we're finding here is we've got a p-value of 0.379 and 0.012. So the B12 seems to be significant. We already know that there's going to be an interaction term here, so we're not going to jump the gun on making any conclusions, but I do want to show you the link between the ANOVA and the regression output. So if we pull the regression output for the same data, just using indicators for whether they got antibiotics or not. So here's the regression output. Oops. You know what? Wait.
Can you put them side by side instead?
Yes, I can. I'll have to make them smaller though.
Yeah, I think that's okay.
But that looks better, doesn't it? Yeah, nice. So here, I'll just do this. Okay. And then here's our regression. I left a little blue there. Okay. So our regression output, we're using A for antibiotics. So A is if they got antibiotics. So A is yes, antibiotics. And B is yes, they got B12. So these are binary variables. So we've got this built-in indicator here. And so if A is yes and B is yes, then they got antibiotics with B12, right? And so if they didn't get antibiotics, this would be 0, and then they only got B12. And if they didn't get B12, then our weight gain would be 7. So again, we will be able to derive from the coefficients, we'll be able to get to these means. but it's going to be a little bit trickier, right? But one cool thing to notice is that you've got these p-values, 0.379 and 0.379 and 0.012 and 0.012. I think that's the most notable thing, is that you get the same p-values for essentially the slopes of A and B as you do in the Anova for antibiotics in B12. Okay. There's a bunch of other links, but I would say that that's kind of the coolest link that you can find. Okay, how do we get to from these coefficients or from these means to these coefficients? It's actually going to be easier if we use from the means to the coefficients. And so from the means, oops, means to the coefficients, we're going to have, if we just focus on the antibiotics, we've got a mean of no, which is 20.5, and a mean of yes, which is 28.5. The difference here, the difference is 8. Right? And so that's this 8 that's here for antibiotics. So it's a little bit different, right? But kind of that's how it works. So if we did the same thing for the B12, if we've got no, we've got a mean of 11, and yes, we've got a mean of 38. So that's how we're going to get this difference of 38 minus 11 puts me at 27, which is that, whoops, that one there. So a little bit harder to see the connection between the coefficients and the means, right? But they are there, it's just a little bit trickier. Okay. For if we've got an interaction term, then let's say we've got this interaction term for the pigs data. With interactions, or interaction, our Anova output, and I'll put it side by side with our multiple regression output. Okay. With interaction, so here's our Anova and here's our regression. Let's make some connections here. What's different is that these p-values don't match anymore. But the reason for that is because the interaction term, right, we're not able to tease out the interaction term here. So the p-values will be different, but we'll still be able to find the estimates, right? And so let's see here. The means for no was 19, right? And so what we said was A of 0, that's no A, and B of 0, that's no B12. So no antibiotics, no B12. That's our reference group, right? So here, no A antibiotics, oops, antibiotics, and no B12, is the reference group. So the reference group is the constant, which is going to be the no has a mean of 19. So that's our constant here. So let's see. No, mean of 19. 19 is the constant. This is our reference group. Okay. If we keep going, right, then the no antibiotics, but yes on the B12. So now we're going from the constant and yes on the B12, right? We've got 19 plus 3, which puts us at 22. So here, no yes must be 19 plus 3, which is 22, right? That one here. We don't have to worry about the interaction term until they're both there interacting with each other, right? So it's not until yes, yes that we've got this interaction term. So here, yes, yes, now we've got this interaction. I guess I can do that last one. I'll do the yellow. So the yes, no is the control plus A. So, and I guess I can't use yellow. It's very hard to see. But it would be 19 plus negative 16, which is 3. Let's go back to this interaction. So we're expecting to see a mean of 54. And so how we're going to get that is we're going to have 19 plus yes on the A, which is minus 16, plus yes on the B, which is plus 3, plus the interaction term, which is plus 48. So if we try that, hopefully we land on 54. So we do 19 minus 16, oops, 19 minus 16 plus 3 plus 48, 54. So a little bit trickier when we're dealing with this interaction term, right? But we can still use the coefficients to figure out what the estimates for the means are. I think that's all that's interesting. Not surprisingly, your R-squareds and your adjusted R-squareds stay the same, but they're always from regression, so that doesn't really make a difference. What else is interesting here? I think that's about it. Okay, so that's just the relationship between Anova and regression. You can get these estimates. You can use the regression output to get these estimates. And your conclusions will always be the same, right? And so, yeah, nice. Any questions about that? No, it's kind of a weird section. No.
I was thinking on if you're using Anova, then the way you state your conclusion. Well, the conclusion is the same, but what I mean is how you approach how to state your conclusion.
So for the Anova, right, we're saying that there is a significant effect if we're using, well, even antibiotics and B12, but definitely there's an interaction here. Here on the regression side, we would conclude the same things, right? And so here, B is not a significant coefficient, but because A, B, so the interaction of the two is significant, we would include it in the model. So you're right, how we kind of word our conclusions I would not worry about it too much because it's going to be very similar. But here we're talking about effects, right? And here we're talking about just kind of the coefficients and the slopes. And so that would be the only difference. But I would probably say that your conclusions are going to be the same. I can't really think of how your conclusions would be any different from each other. But yeah, that's a good question. Make a note to myself more than anything. But
yeah, well, just as you said, they are saying the same thing, right?
yeah,
Yes, that of course, if you do it in ANOVA, straight away you would say that antibiotic and B12 is significant and there is an interaction, right?
that's right. Yeah,
Right. But for the regression, you would say that, well, yeah, well,
yeah,
B is not there.
yeah. But it is significant in AB, so that's why we would keep it in there.
Okay.
Right. So because it's significant in AB, then we have no choice but to keep it in there. Because if we remove B, then there would be no AB, but we already just
Yeah.
found that
Yeah.
that's significant.
But
Right,
if
so,
you remove AB, then both A and B are significant, right?
probably. What did we see here? Oh, is this the same data? I think so, right? If we removed the interaction term, we actually found that A was not significant.
Yeah. Yeah.
Right? So that would be the difference. But that's the same conclusion that we landed on with just the two-way ANOVA without the interaction. So here you would land on the same conclusions, and here you're essentially landing on the same conclusions, just with different p-values.
Okay, so it means that you would include B because B is interacting with A which made it significant.
That's right. Yeah.
Okay.
Good. Good. Yeah. So here, this is not something that I would expect you to do or use. Once you've decided to use an ANOVA, there's no reason to use regression unless you want to pull these coefficients. If you've done an ANOVA, just stick with an ANOVA, right? So you don't have to do both. There's often, like if you've got a categorical variable in there and that's the variable of interest, then an ANOVA is the obvious choice, right? Then you should be using an ANOVA. Here, it's just illustrating that you could use regression if you wanted to. Right? And it just depends on the situation. So, last section in chapter 8, last random section that we're going to talk about. Again, it's one of those things that is its own, course essentially. But 8.8 is the analysis of covariance. Analysis of covariance, which we can abbreviate ANCOVA. So an ANCOVA comes about if you've got a regular ANOVA situation. So you've got a numerical response and you've got a categorical factor of interest or variable of interest, but you've also got some sort of continuous numerical predictor that you want to fit into the model somewhere. So if we would like to model the relationship, between a continuous variable, I'll even add a continuous response variable, just to be sure, and a categorical explanatory variable, and a categorical explanatory variable. But we suspect that there may be another quantitative variable, so numerical variable, affecting the outcome of the analysis. Okay, so, but we suspect that there may be another quantitative, so numerical, quantitative, numerical variable affecting the outcome of the analysis, the outcome of the analysis. We need an analysis of covariance model. We need an analysis of covariance model. Okay. So here, the only new thing is that there may be another quantitative variable affecting the outcome. So we want to have a classic ANOVA situation, but we want to incorporate a numerical factor. I don't want to call it a factor, right, because it's not categorical, but we've got a regular ANOVA with a numerical factor. I'll put factor in quotes because it's numerical, so it doesn't really have factors, but it's how we're going to incorporate a numerical variable into an ANOVA is using an ANCOVA, analysis of covariance. And so a continuous variable, so here we're going to define what we call a covariate, and the covariate is this quantitative or this numerical variable that we want to incorporate. So here with a numerical factor, which we call a covariate. So here, let's define it. So a continuous variable, and it's an explanatory variable, so I'll use X and then subscript C just to show that it's continuous, not of direct interest, because that would probably involve some sort of regression instead. So not of direct interest, but that may have an effect on the relationship, that may have an effect, on the relationship between the response variable Y, and the factor of interest. And the factor of interest is called a covariate. So the ANCOVA model, which is besides the conditions as far as we'll go, so the ANCOVA model looks like this. It's got y, and it starts off as a regular ANOVA with alpha I or tau if you want, but we'll use alpha I plus beta times xc plus the adjusted errors. So where I'll say where xc is the covariate, right? So that's numerical. And the adjusted errors, so E adjust, or the, is it an epsilon, I think, is the error term adjusted for the covariate. So adjusted for the covariate. This is not something that we are going to dive into, right? But because this is continuous, then unlike the blocks, if we just had a block, then we said, well, the block absorbs some of that error, right? And so you argued on test 2 that, well, introducing blocks is actually going to reduce the errors, right? Because it absorbs some of that variability, right? So here, because this is continuous, it's going to be a little bit trickier than with just the blocks. And so we've got this adjusted error term. Not something that we need to worry about, but that's the model. So the conditions for ANCOVA, just mostly for completeness, is a little bit weird. So here we've got an ANOVA essentially, right? So the conditions for ANOVA have to be met. And here we've got essentially regression, which means that all the linear regression conditions also have to be met. And we have to check that there's no interaction between the factor and the covariate. So those are your conditions. So you're checking ANOVA conditions, you're checking regression conditions, and there can't be any interaction between the two. So that's kind of weird. Just something to know and keep in mind, that there are different conditions for ANCOVA. So all ANOVA conditions are met for y with the factor of interest. For y with the factor of interest, interest, all linear regression conditions are met for y with the covariate xc, but also that there is no interaction. There is no interaction between the factor and xc, between the factor and xc. Yeah. Like I said, ANCOVA is a huge, probably another at least half a course. So we're not, we're not even scratching the surface here, but this is the general lay of the land. And so just knowing this, that you've got this kind of combination of ANOVA and regression, right, is going to dictate your conditions. If you're interested, I think example 8.26 gives a nice kind of quote unquote full example. And so if interested, see example 8.26 in the textbook, for a full example, right? Again, not something that I'm testing you on, right? I'm only testing you on things that we've said in these notes today and next day. But just down to the wire, but that's all I've got. So that's the end of chapter 8. And then next day we'll do chapter 9 all in one day. But luckily it sounds like you guys have seen logistic regression quite a bit. So that's good. So it might just be a nice refresher and finally back to something that you are familiar with. Any questions? Let me see.
No.
No questions? All right. Nice. All right. Well, then that's all I've got for you. Yeah. I
We
guess.
have the practice questions. Review.
Oh, for practice questions? Well, you've got those extra practice problems from Moodle, right? Those Moodle quizzes. And I think so. Yeah, definitely focus on the notes. So only things mentioned in the notes. Oops, I mention in the notes. Oops. Are, let's say, testable. Trigger happy. Yeah, so oh, it went to sign only, but hopefully you can all see it because I'm sharing my screen. All right. Yeah, so any other questions? So just focus on the notes, right? And everything that we've talked about, that's what I'm expecting you to know. And even some of that stuff was extra. So, but yeah, just focus on those. Any other questions? No? All right. Then I wish you all a great weekend, rest of the week, whatever it is for you. And I'll see you guys on Monday. All right. See ya. Oh. Thanks, guys. See ya.